Yes.
Okay. Um, cool. Yeah. Thanks for having me and for sticking around through to the end of the day. Um, what I want to talk about today is a sort of approach to solving decision-making problems by building little symbolic models on the fly. And hopefully that'll set up a more general conversation about the role of kind of symbol processing systems in the modern AI landscape. So let's imagine an AI researcher who's trying to build a system that can do these kinds of tasks in some sort of kitchen environment. Um, and let's imagine that our researcher already has access to a robot platform with some basic perception and action capabilities. It has a structured scene representation that can do some object and property and relation detection. We have some, maybe mid or high level actions for doing navigation and pick and place and things like that. And let's imagine finally the year is 1974. How are we going to build this robot? Well, the high level structure of the program that our researcher is going to write here might look something similar to what we might build today, right? There's going to be some language understanding, there's going to be some planning, and then we're going to take that plan that we generated and we're going to send it off to the robot. Um, we're going to build tools to do symbolic language understanding. We're probably going to require the user to generate text from some restricted subset of language, to speak in a controlled grammar or something. And at the end, we'll have some symbolic system that maps from language to logical forms representing user goals. And when we think about how to do planning, our researcher in 1974 is likely to try to do this symbolically as well. I don't even know how much they, sort of teach this stuff to incoming grad students anymore, but the way classical planners work is you define a set of high-level actions. In our kitchen environment, these might be things like slicing a food item or transferring an object from one place to another. We're going to write down the preconditions and postconditions of each of those actions in some sort of formal language, right? The things that need to be true in order for us to be able to execute the action, the things that are going to be true in the environment afterwards. And then we'll search with our favorite tree search algorithm for some sequence of actions that is well formed in the sense that by the time we take an action, its preconditions are satisfied, and eventually we do whatever it was that was specified by the user's original goal as one of our postconditions. Now, how well does this system work? The year is 1974. Perception and control are terrible. We have none of the robustness that we've come to expect from modern vision systems. We're almost certainly working in a blocks environment. Maybe we're not even trying to do this in the real world and doing this all in simulation. But within that blocks world, we can actually handle some, I think, pretty remarkable forms of generalization. The cool thing about these symbolic planning methods is that if you have described the world correctly, and if you have the compute power to sort of solve your planning problem, you can actually generate arbitrarily long plans, arbitrarily complex plans, starting from arbitrarily complex initial configurations of the environment. Now, I just said that we can generalize to complex plans, but generalization from what? And what does generalization even mean in this context, given that we're working with a rule-based system? So to the extent that there's a learning algorithm at play here at all, it lives in the head of our researcher who is building this system. The data for this learning algorithm is whatever set of examples she was thinking about or sort of playing with while she was developing this system, plus whatever background knowledge she had about kind of the world in general before she started trying to build this particular model of this particular family of tasks in this environment. And the number of problem-specific examples that she has had to think about while doing this is probably on the order of tens or hundreds. And in that sense, this learning algorithm is incredibly sample efficient. And it is meaningful to talk about generalization, in this case, to just more complex examples than she ever thought about or reasoned about while building this robot. Another nice thing is that we can understand at a sort of relatively deep level how this system works. It's code. It's probably not that much code. One person wrote it all. And we can take that code and use it to prove things like this robot is never going to leave the refrigerator door open in this environment, or if the environment contains a stove and a refrigerator and a knife, then and only then it is possible to satisfy every user goal and some delimitable set of user goals, and so on. Okay, so these are nice things about the system that we built. On the other hand, if the examples that our researcher thought about here were data, then the learning algorithm that she applied to sort of derive the system from this data was terrible, right? It probably took her several years to build the system. Maybe we give her a PhD at the end of this procedure for her trouble. And in practice, a large part of the time that she spent building this symbolic robot planning system was probably time spent thinking about kitchens. Not about sort of planning in general or about robotics in general, but this specific environment, trying to figure out what objects and what states we need to keep track of, what kinds of high-level actions we're going to need to make available to the planner, what the preconditions and postconditions of these kitchen-specific actions are, and so forth. Is being sliced a property of a potato, or does slicing turn a potato into a collection of new objects? What's the right level of resolution for that representation, and so on. And this is going to be an issue because if the world or if the task distribution changes in only small ways, the system isn't going to work anymore. And the changes that we might need to make to it to get it to work again might be non-trivial, right? What happens if we decide that we need to explicitly model doors? Now we need door manipulation operators. We need to change all of our preconditions and postconditions and so on. And some of these might in turn require different low-level controllers, et cetera. So the generalization of the system within problems is great, but as soon as we try to generalize to a new problem domain, or change the sort of problem definition at all, then the generalization becomes terrible. Okay, good. So the year is actually 2024, not 1974, and the story looks very different now. If we're going to build a robot, we need to do language understanding. And now language understanding is easy, right? As we've been seeing in several of the talks today, we can either get high quality representations from some off-the-shelf language model, or even translate from natural language into a formal goal representation by just prompting a big LM to act as a semantic parser. Our system needs perception, and perception is pretty easy now, right? We can take an off-the-shelf vision model, something like the segment anything model, and we can recognize all of the objects and classify all of the relations that we care about, at least provided that we're in a fully observed environment or can do some very simple state tracking on top of this. Our system needs the ability to do low-level control. And if we're willing to go out and collect a gajillion demonstrations of whatever sort of specific motion primitives we want to make available to this model, then maybe even without a human in the loop, we can get reasonable controllers if we're willing to just like do enough RL or gather up enough supervision. But this high-level planning step, right? This problem of taking a high-level goal and figuring out what long sequence of composed motion primitives is actually going to accomplish that goal is really hard. There's been a huge amount of interest in the last couple of years in language-based planning work, really starting with work in the NLP community from SIHR and colleagues, my student Pratyusha Sharma's work, and sort of bigger system demos from other places as well. And, I guess I want to claim right now that none of these language-based planning systems really work all that well in complex environments or with very, very long horizon tasks. And they definitely don't give you the kinds of generalization or the kinds of guarantees that our old school, 1974 robot planning system provided. And in particular, right, we have no idea what's going on under the hood in these systems, or when they're going to fail, or any ability to predict ahead of time, what kinds of requests they're likely to be able to satisfy and which ones they can't. So a lot of, sort of actual robotic systems out there today that are trying to do these kinds of long horizon tasks still rely on manually defining features and skills, and generalization at the task level is still kind of painful in the same way that it was in our hypothetical older version of this story. So when we talk about the history of artificial intelligence these days, I think there's a popular narrative that all the sort of deep learning stuff won because symbolic systems just don't work, right? That they can't be made high recall enough to be useful for any kind of practical application. And in some problem domains, this is clearly the case, right? Good luck writing down a sort of formal definition of a chair in a way that recognizes all of the objects that we're describing here as chairs or as dogs or anything like that. But I think in many other domains, the lesson is actually a lot subtler. That these kinds of symbolic systems can be made to work, sometimes even better than these big end-to-end representation learning approaches, but it's just not worth it to do that. In a lot of these symbolic approaches we've been talking about, the sort of human intellectual effort required to build one of these systems scales linearly in the number of different problems, right? We have to do a bunch of novel work in every problem domain that we want to move to. Whereas in, sort of modern end-to-end ML approaches, the incremental effort that we need to take our system that, steers robot hand number 1 and get it to steer robot hand number 2 instead is small enough that it might as well be constant. So, machine learning, and I guess especially deep learning, unlike classic symbolic system building, lets us adapt very quickly to changing goals into a changing world. But, like we were saying before, that comes at a cost in sort of generalization, in interpretability, and robustness. And so what I want to sort of talk about very briefly here in the piece of work that I want to highlight in this talk is techniques for building symbolic systems that exhibit sort of deep learning-like scaling in the sense of developing a general purpose technique that we can reuse automatically across problem domains and not just individual problems. And what we want basically is to build some sort of black box that's going to replace our 1974 graduate student and do the work of sort of developing informative examples, figuring out how to represent them symbolically, and integrating these symbolic representations into an end-to-end planning system without requiring a human in the loop at all. The year being 2024, right, it will surprise nobody here that the way we're going to do this is to use some kind of large-scale language model pre-training. But I think, even back in 1974, right, the long-term solution, or it should have been clear that the long-term solution had to look something like this. The data that our grad student was using to build her system includes both a set of individual domain examples and everything else that she learned in her entire life. And if we think about where to get access to that kind of knowledge, the kinds of things that our researcher is bringing to bear when she's working in this new problem domain, a lot of that knowledge is contained in language, in the books that she read, in the lectures that she attended, in the papers that she wrote, and the sort of the conversations that she had in the course of constructing the system. Good. So yeah, what I want to present now is like a sort of vignette of a system that roughly implements this vision that's using big LLMs to interactively build symbolic systems tailored to a domain of interest, and then give us all of the sort of nice properties of symbolic systems to do things that we can't do with language models alone. This work was led by MIT PhD students Leo Wang, Jiayuan Mao, and Pratyusha Sharma. Okay, so how does our hypothetical grad student on the first day of the project figure out how to build a good kitchen robot? I want to say right now, robot in scare quotes, we're sort of starting to move some of the stuff onto real like Boston Dynamics spot systems, but everything I'm going to show you today is in simulation with AI2 Thor. Okay, so maybe our grad student here starts to write down some examples of the kinds of commands that she'd like the system to be able to execute. And then maybe she starts to write down some of the plans that would be associated with each of these things, expressed in terms of sort of hypothetical high-level actions that might be involved in those plans. Well, what's an action? Like we were seeing before, an action has a name, it has some preconditions, and it has some postconditions expressed in terms of whatever it is that we can sense in the environment. So let's forget actually about all of these plans for a minute, and just for each of these actions that we wrote down, take a minute to write down what we think it means to put in terms of things that we can detect with the sensors that are on our robot, right? The ability to detect whether it's holding things, the ability to detect whether locations are empty, and so on. And we can do this for all of our other actions as well. And now that we have these, let's go back to our original goals and see if we can actually come up with plans that satisfy those goals. And maybe in the course of doing so, we discover that we had some mistakes in our original plans, right? Here we said we were going to start by chilling the wine, but the way we've implemented our high-level actions, we first need the robot to be holding the wine first. And so, maybe we need to amend this plan to include some extra, actions as well. And that's fine, right? Because now we can verify automatically whether our proposed plans work or whether we've made a mistake in writing the plans or in defining the operators in terms of which these plans are expressed. Okay, and so maybe we continue this refinement process until we have a good set of symbolic operator definitions and a good set of plans. Are we done? We're not quite done, right? These sort of operators are totally abstract, and we need some way of getting our, robot motors to spin in a way that executes each of these high-level operators. And maybe we can do this by writing down a fixed set of actions or a fixed control policy. Maybe we can manually define a little, LQR controller or something like that. In our hypothetical example, maybe our student discovers that chilling is more complicated than she realized, and she can't figure out how to write down just a sequence of low-level actions that do it all from whatever the starting configuration is. She goes back to the drawing board and comes up with an even finer grained set of high-level actions that will eventually allow her to implement a low-level controller for each of them. So maybe we turn the original controller into something like this, and she can figure out how to build atomic policies for getting and opening and putting and so on. Okay, so what we've described so far is the sequence of actions that a human researcher might take to build a symbolic controller. What would it look like now to automate this process? here's a sort of flowchart of what we were looking at before. We're going to start by defining some symbolic action representations. We're going to look at these symbolic action representations and use them to write down some hypothetical plans. And then we'll refine our action definitions and refine our plan definitions until those things all look right and are consistent with each other. And once we have plans that we're satisfied with and actions that we're satisfied with, we'll build a low-level controller for each of those high-level actions in a way that allows us to ensure that it actually satisfies all of the post conditions. And maybe in the course of doing that, we need to do some refinement back to plans or to actions as well. Okay, so how might we automate this process? Well, the first of these steps, right, generating these symbolic action representations, is really just about generating some code based on a high-level natural language description of our goals. And this is the sort of thing that modern code language models are amazing at. So let's just do this with an off-the-shelf language model, prompted to generate some formal definitions of actions. What are the preconditions and postconditions and parameters and so on of doing something like slicing? Okay, well, here's the bit of our process that looks like planning. And once we have our symbolic action definitions defined, we can solve this next stage of writing these plans just with off-the-shelf planning tools. These planners need symbolic goals in addition to our symbolic action definitions, and it's easy for language models to generate those as well. So once we have goals, once we have operators, we can try to generate plans. We can figure out whether the plans actually succeed, and if not, we can go back and try to refine our symbolic action definitions. And the last step here involves taking these plans and actually turning them, or taking these actions and turning them into controllers that we can execute on our robot. In our hypothetical scenario, our researcher was doing this by hand, but let's talk about how we might automate this. Once we have a plan, right, we don't now know not just the sequence of high-level actions that we might need to take in order to accomplish it, like in these sort of standard language model planning procedures. We actually know what the environment needs to look like at every step along the way, because we know what our planner expects to be true as a result of each of these actions. And so after we've sort of completed the open action on the fridge, we know that the fridge should be not closed. We know that after completing the get action on the wine, the robot should be holding the wine. And so what we have now is something that looks like a really nice scaffold for doing reinforcement learning. We can try to learn a policy for each of these low-level actions, where the reward function for that policy comes not from satisfying the sort of long horizon goal that the user specified, but just for satisfying the post conditions of the particular action that we're trying to learn a policy for. And so really what all of this symbolic scaffolding that we've been building has led up to is a way of turning this like long horizon sparse reward RL problem into something with a nice dense smooth reward that gives us lots of intermediate quantities that we can verify along the way. And once we have this, right, we can just throw this at a standard RL algorithm, however we want, and get maybe little controllers for each of these high-level actions, or even just one big controller that, takes as input like an embedding of the word open or the word get or whatever, and executes it in sequence. Okay, so here's another look at the sort of overall system architecture again. We have a language model. It generates some symbolic high-level action definitions. A symbolic planner turns those things into plans. An RL algorithm uses those plans as a scaffold to learn a little modular policy with a dense reward. And if any step of this process fails, it can go back to the previous one and ask for refinements of the symbolic representations, either the plans or the action definitions, in order to sort of try to make that failure go away. And importantly, right, failure could happen either because our symbolic model is wrong as a model of the real environment that we're trying to do RL in, such that it sort of doesn't cause the post conditions or the preconditions that need to hold for RL to succeed. Or it could fail just because we're asking this low-level policy to do too much all at once, to solve a sort of impossible exploration or inference problem that we can't fit into a fixed size neural net or other procedure. And so what we're going to get, if we can run this procedure end to end, is a sort of library of actions, a library of controllers that are tailored both to the dynamics of the environment and the limitations of whatever low-level policy learning procedure we're running. So if there's a piece of environment state that's relevant to the distribution of goals that we care about, only then are we going to put it into this model. And if there's a planning problem that's too hard for that RL step to solve, only then are we going to try to offload that planning problem onto the symbolic model instead. And so if we're in an environment where just like DeepRL can do everything, this architecture is going to let DeepRL do everything. And otherwise, we're going to learn automatically a little symbolic world model that's just expressive enough to do all of the things that our DeepRL approach can. Okay, so to start to wrap up and hopefully leave a couple minutes for questions here, how well does this work? I'm going to show some numerical results on 2 data sets because we have to show some graphs in this talk, the Alfred environment and a sort of mini Minecraft environment that we built in-house. For those of you who've worked in Alfred before, this is not the usual setup here. At training time, we have access to high-level natural language goals. We have access to an environment-generated sort of sparse success criteria. And like a lot of recent work, we're assuming we have a low-level navigation policy, but that's it. We have no demonstrations at all. We're really just trying to do this all via reinforcement learning. Okay, so here are some bar graphs because we need to show some bar graphs. And the main thing is that the approach that I've been describing, which we call ADA for action domain abstraction, is good. And certain other things that use LMs to solve planning problems in other ways are not good. I think maybe the most interesting or main thing that I want to highlight here is that these Minecraft results we generated like literally the day we were, or maybe a couple of days before we were submitting this to the conference, that Codebase was developed totally autonomously, and nevertheless we were able to do really well on it, taking a system that we had been, sort of developing and benchmarking just in this Alfred environment. So think of this as really some evidence that we are getting ML-like scaling. We've developed a general procedure in one environment and immediately had it transfer to another environment and generate, different kinds of symbolic representations tailored to that world as well. I can show you a video, but it's going to look like any other video of doing things in Alfred, so it's probably not all that interesting. Maybe a more interesting thing to look at here is some of the operators that are actually recovered automatically by this procedure that I've been describing. And the cool thing to notice here is that, one, they are similar to, but generally not identical to, the actual formal representations that people have developed for these AI2 Thor environments. And two, just that they're like quite complicated, and that the language model that's writing code here is able to write code that's pretty sophisticated and that captures a pretty broad set of sort of complex preconditions and complex postconditions of actions. Okay, so to wrap up here, what did we learn? Planning is still really hard. I think planning is still, just like a fundamental thing that we haven't figured out how to do inside LM type architectures. But writing planning representations or writing, representations for sort of a formal planner isn't hard. And so we can take big models that were trained on code, use them to generate these kinds of formal representations on the fly, formal representations that are just small enough, or I guess just big enough to solve one planning problem that we care about, use it to solve that problem, and then throw it away. And an even higher level point here is that even when these big LMs can't do formal computation internally, we can use them to sort of automatically formalize the tasks that they can't perform internally. And this turns out to be a really powerful way of getting a lot of the nice sort of generalization, safety, interpretability properties of symbolic systems, while avoiding the brittleness and the lack of generalizability that's traditionally been a problem for this system. Okay, and why am I talking about any of this at a workshop on, sort of social intelligence and human-robot interaction and things like that? I think one of the most important insights here is that the way to get these little domain-specific formal models that seem to be quite useful is to start with domain general training on, sort of human background knowledge. And a lot of that background knowledge, maybe unsurprisingly, is expressed not in the form of explicit formal representations, but free-form natural language instead. So, I think in the broader landscape of social robotics, this ability to learn new things from language and to translate information that's communicated sort of informally and turn it into something, sort of nice and crisp and logical that we can do machine reasoning on, is a really powerful tool and something that I think we can do in a way that was hard to imagine even like 5 years ago. But the other piece of this equation, of course, is not just learning from people how to act autonomously, but to learn how to interact in environments where, sort of people are acting autonomously as well, as the previous talk emphasized, right, these sort of models are good at doing their kind of squishy, non-formal reasoning about social behavior and about the behavior of social agents. And so I think there's still a big, really interesting open question about just what the right way of putting these two things together. Can we build, sort of little on-the-fly symbolic models of behavior as well, or do we need to really sort of rethink what planning looks like when we have good models of agents that are hard to make talk to, some of the more formal methods that I've been talking about today. Yeah, and with all that, I will wrap up. As always, all the credit goes to the students who led this work. I'll note that Zach here is going to be applying to grad programs next year and is awesome. So keep an eye out for him. And thanks very much for having me.
Right. Thanks so much, Jacob.
Yeah, thanks a lot. I think there's a question from Charlie. How can we apply this framework in environments where interaction is expensive, for example, physical world, and feedback from online RL that may be not be feasible?
Yeah, so I think there's a couple of different ways to think about this. One is that this is actually, and I guess I didn't really talk about this, but pretty sample efficient in the sense that, because the sort of LM is doing most of the work of giving you nice intermediate checkpoints for your planning problem, the work that the RL system has to do is actually pretty easy compared to what you'd see in a normal deep RL context. So I think, one possibility, or one way of answering that question is just that I think, something that looks like this is exactly the right way to deal with embodied environments where that kind of interaction is expensive. But another piece of this, of course, is going all the way back to the beginning of the talk. Where did this go? Sorry. That in parallel to all of this, we are getting good at large scale pre-training for these at least like short horizon motion planning tasks. And I think, when I imagine how we're going to build the version of the system, maybe even like 12 months from now, it involves not doing kind of RL from scratch to learn each of these low level controllers, but maybe starting with some sort of pre-trained like general purpose manipulation policy that just needs like a little bit of fine tuning, or maybe even just like a little bit of prompting to complete these low level goals.
Mm-hmm. Yeah. I have a question. I think this is a really cool idea, like the symbolic action representation. So in the first part, there's using language model to generate a set of like post and pre conditions. So how do you control the language model that can generate a meaningful like conditions that are relevant to your task? Because the language model can generate like any type of text, and how to make sure that this is relevant to the given task, and what if there's some like errors caused by the language model?
Yeah, no, that's a really important question. So one, I guess, sort of important thing to say about the system that I've been describing now is that we assume that the set of sort of sensors available to the model ahead of time, the set of predicates that you can use when defining, or predicates and relations that you can use when defining your action representations, that's fixed ahead of time. And so we're really saying to the language model, hey, write me a little strips operator or whatever for doing this high level task with this natural language name using this set of sensors with these sort of meaningful natural language names. And that already kind of puts you in the right neighborhood of things that you expect to be at least useful in your environment. But a lot of the time, the initial definitions are still wrong, or still, leave out irrelevant things, or, like hallucinate preconditions that aren't actually relevant to the dynamics of this environment. And so the important thing there for correcting those is just having this feedback loop, right? That you can say, okay, if I had this action definition, this would be my plan, and this would be my reward function. Can I actually learn against that reward function? And if not, then we have to go back and try again. And for the results that I was showing, it takes like 3 or 4 rounds of trying again to actually get to good results on most of these tasks. So maybe the main takeaway there is that that sort of outer loop RL over the definitions of this kind of on the fly symbolic world model is itself in principle a really, really hard RL problem, but the language model is a good enough prior that you can get close enough to the solution that there's then like a reward signal there to hill climb on. One, I think, really interesting and really important extension of this stuff that we're talking about right now is to say, well, what happens when we're in a scenario where we don't know what the set of sensors is ahead of time, where we're starting with just raw pixel data or something like that, but maybe we have an off-the-shelf segmentation model or whatever that we can cause to test, or maybe even a general VLM, right, that we can ask arbitrary questions about the state of these images. And there now, you have a kind of another latent variable in the system, which is the set of predicates that are available to you as well. And I think that's a harder learning problem and one that we're still figuring out how to solve.
Yeah, that's very interesting. Like the iterative refinement to correct the errors and use additional models to provide us external